Hey Math Kids, today we're going to talk about infinite geometric series, and we are in chapter 5, section I in your book, and there's only one example, and then there's a statement. I wanted to explain the statement a little bit before we got into the example. So the first part that's written in yellow, it's worded a little bit different, but this is essentially what it says in your book. It doesn't really say anything about divergence, and I just wanted to show how this was related to the finite geometric series that we talked about in the previous video. So this thing written in blue is from the previous video, and we can see some similarities. We have a 1 minus r on the bottom, we have a u1 on the top, but then this thing disappeared. So what I'm going to do is I'm going to plug in a really, really big number for n. So I'm going to say like 3 billion. I'll just write it out like that with a word. Okay. And in a practical sense, 3 billion is going to do the same thing as infinity. It's going to create a very, very, very large number. And so if we have r raised to the 3 billion, it depends on what r is on what happens. So let's take this first, or the second case, where if r is greater than 1. So, I don't know, let's pick 3 or something. I mean, we don't have to choose anything specific, but so it's... Okay, so we have 3 raised to the 3 billion. Okay. And 3 raised to the 3 billion is going to be a very, very big number. 1 minus a very, very big number is just going to be a negative, very big number. So essentially, if we are u sub 1 times very large over negative 2, in this case, it would have been a very large negative number. So all of this, if we take a very large number, times it by something, doesn't matter the number, it's still going to be a negative, very large number. And then if we divide that by negative 2, negatives will cancel, but a very large number divided by 2 is still very large. And so if we go back to this 3 billion and we thought of it as infinity, let's just think about that for a second. So it's u1, 1 minus r, and this is the case where r is more than 1, r to infinity over 1 minus r. R to infinity is essentially going to be infinity. So 1 minus infinity, u1 over 1 minus r. 1 minus infinity is just going to be negative infinity. So we have negative infinity u1 over 1 minus r. Negative infinity times anything is either going to be negative infinity or positive infinity. So we'll just keep it at negative infinity. And then negative infinity divided by any finite number is either going to be negative or positive infinity. So we can keep it at negative, or it might become positive depending on the sign of the number. So those are just two ways to kind of think of this bottom statement. So if r is greater than 1, it diverges to positive or negative infinity. So we're not going to really talk about it in this class. That's why the book leaves it out. Now the top one, I want to talk about why it doesn't do that. So u1, 1 minus r to the n over 1 minus r. This is our s sub n. Okay, now n is still going to be infinity, but what happens when we raise something, so something that's less than 1, so like 1/3. If we multiply these together, we get 1/9. And if we multiply it by 1/3 again, we get 1/27. And that bottom number is just going to get larger and larger and larger, so it's going to go to infinity. But when we have 1 over infinity, it actually goes to 0 because our number is getting so small that eventually it's going to be essentially 0. So we take out this part because it went to 0. And that leaves us with u1 times 1 over 1 minus r, which is just u1 over 1 minus r. And that's our sum. If we go all the way back up to the top, that's the same thing we had right there. Okay, now something that's left out, we have less than 1, greater than 1. What happens if we have exactly 1? So what if I plug in 1 for r? Well, on the bottom, we're going to get 1 minus 1, which is 0. That creates division by 0, so we can't do it. It doesn't make sense. Okay, hopefully that helped you understand that. Now we're going to move on and do the example that they have in the book. And then I actually want to show you one more thing that's not in the book, but I think it's cool. So we're on example 31, and it says write 0.7 repeating as a rational number. So first we're going to write it as a series. So I'm going to write this out like this is what this means, right? So I can also write that as 0.7 plus 0.07 plus 0.007. So we're just kind of adding each 7 in there. So those zeros are like placeholders. Okay, now this we can write as a fraction, 7/10. This we can write as 7/100. Whoops. This we can write as 7/1000. And that's actually how we pronounce these, right? So this is 7/10, 7/100, 7/1000, and so forth. Okay, so we have this going on. Now if we think of this as a geometric series, we have our u1 is 7/10, our first one, and each time we're just dividing by 10, and so our r is 1 over 10. Now because our r is less than 1, we can use that finite series formula. And now we just plug stuff in. Okay, we do a little bit of simplification. We think of 1 as 10 over 10. So that gives us 9/10. So we have 7/10 over 9/10. That looks kind of confusing, but what I'm going to do is I'm going to take all of this and I'm going to write it as 7/10 divided by 9/10. 7/10 divided by 9/10. And we copy dot flip. So we write 7/10 times 10 over 9. Just flip the second one, turn it into multiplication. I'm sure you've learned that before. And then from here, use whatever simplification techniques you can. I like to cancel these two 10s, and then we're left with 7/9. So if we go to a calculator, just want to prove this to you. Once again, it's frozen, so let's try that again. Okay, so we got 7/9, and we're claiming that 7/9 is the same thing as 0.777 repeating. This calculator rounds up the last digit to an 8, so it really is just 0.777 forever. And that's kind of a quick calculator proof right there. 7/9 equals 0.7777. Okay. Now, this can actually be used to prove one of my favorite things to talk about in math. So the fact that 1 is equal to 0.9 repeating. Now, if you talk to people about this, they generally will say, well, yeah, it's very close, but it's not exact. What I'm claiming right now is that these are exact. They're exactly the same thing. So I'll show you. I'll show you a quick little. I'll convince you in one way, and then I'll use what we just did to prove it to you. So most people will agree that 1/3 is equal to 0.3 repeating. People will also agree that 1/3 plus 1/3 plus 1/3 is 1. Okay, if you think of a pie cut into 3 pieces, you put those pieces back together, you get one whole pie. Okay, people will generally agree that 0.3 repeating plus 0.3 repeating plus 0.3 repeating is 0.9 repeating. Okay, since this is 1/3, 1/3, 1/3, it's equal to 1. And therefore, 0.9 repeating is also equal to 1. So once again, they're not close to each other. They're exactly the same thing. Okay? All right, now we can actually prove this with the same method we used on example 31. So we're going to say, basically just write 0.9 repeating as a fraction, or as a rational number. Okay, so 0.9 repeating is 0.999, just a bunch of 9s forever. We can write that as 0.9 plus 0.09 plus 0.009 plus dot dot dot. This is 9/10. This is 9/100 and 9/1000. If we think of it as a geometric series, we have our U1 that's 9/10, and then we have our common ratio as 1/10. Once again, we're just dividing each one by 10 or multiplying by 1/10. We bring up our formula. So we have 9/10 over 1 minus 1/10. We think of the 1 as 10/10. We subtract 1/10. So the bottom of that is 9/10. The top of that is 9/10. Any number over itself is 1. And so we proved that that is equal to 1. If you feel like that was a little too quick, we can just do the same thing. 9/10 divided by 9/10. We flip the second one over. Multiply the top, get 90. Multiply the bottom, 90. 90 over 90 is 1. Okay, if you need additional help, come to Math Lab. But for now, calculator.